Welcome to the lecture number 6 of numerical solution of partial differential equations, and we are still discussing parabolic PDEs, and in parabolic PDEs we are discussing of course heat equations, and in this lecture we will discuss fifth method to solve parabolic PDEs or this heat equation. This fifth method is very famous method and it is implicit method, and the name of the method is Crank Nicolson method. So we have discussed so far these three explicit methods, and we also discussed first implicit method in lecture number 3 of this course. And now we are discussing second implicit method, which is known as Crank Nicolson method. Okay, in Crank Nicolson method, we take the average of central differences at time level n and n plus 1, and we basically do not apply forward difference on time derivative. What we actually do is, if I go to the book, here you can see what we actually do is we form two equations by applying central difference at time level with step delta t by 2. So we apply forward difference with step size delta t by 2, and then at the end we add those two equations like this. uh, with step size half in time, we take the forward difference here, but on the right hand side it's just the central difference of second derivative with respect to space, and then we again take the half step, the next half step, and we apply forward difference, and on the right hand side it's the same. At the end, we add these two equations to get Crank-Nicolson method. Now, the big advantage of this method is that the method is unconditionally stable. There is no condition on method to be unstable or stable. So it is unconditionally stable method. So this is how we discretize equations using Crank-Nicolson method. So this is the first equation, and then we will try to get n plus 1 things on the left hand side. After multiplying it, this is going to be a constant. This constant is different from the constants in previous methods, like there was no 2 in the denominator, but here we have 2 in the denominator. We will say that this constant is d, and then we will try to rearrange the equations, and this is going to be the final form of Crank-Nicolson method, with all n plus 1s on the left hand side and n's on the right hand side. The method is unconditionally stable, and the order of method is delta t squared delta x squared, so we can say it is second order scheme. Now we will solve one example, and then we will formulate the MATLAB code of Crank-Nicolson method. Here we will solve 1D heat equation with alpha is equal to 1. Of course, there is no alpha here, and on the domain x0 to 1 with time greater than 0. These are the boundary conditions, because at 0 and 1 it is 0, and these are the this is the initial condition, which is function of x. So at time 0, at different space steps there will be different values. We have to solve this equation using space step 0.1 and time step 0.01, and we have to find all the values of u for t0 to 0.02, which means we will perform two iterations because this time step size is 0.01. First, let's determine total number of nodes in time and spatial domain. As you can see, in x from 0 to 1 with step size 0 0.1, we will have total 11 nodes. So I'm starting from x is equal to I is equal to 0. So here it will appear 10. And for space nodes, we will start from n is equal to 0. We will go till n is equal to 2 because the time step size is 0.01. And we have to find at till 0.02. Again, there is no restriction. We can go till any time. So this is going to be the mesh that we want to compute. These values, these green values at the bottom, these are known from initial conditions, and on the left and right side, these are the boundary condition values. And this value overlaps, this boundary value overlaps with the initial value. So u at 0t means u n0, which means all values are 0, which means u00, u10, u20, because all x are 0, x has to be 0, and we have total n 0, 1 and 2. And for u1t, since 1 will appear at the last I, and last I has the indices 10, and for all n it is 0. So 0, 1, 2, 10 is 0. ux0 is basically u0i. It will be a function of x, so it will be different for different x values, which is we can compute it something like. You can also see it from the previous videos. We use the same example for them. So these are the initial values. Now we want to compute the inner nodes, the black nodes. In the first iteration we will get these nodes, and in the second we will get these nodes. This is the final discretized form of Crank Nicolson method, and the value of d in this case will be alpha delta t, and we will substitute all those values to get this d as 0.5. Now there will be 9 equations for each because there are 9 inner nodes, so 9 equations for each, and since that there are 9 interior unknowns, so we will form these 9 equations by substituting I values in this Crank Nicolson scheme. So we will start with I is equal to 1, and we will go till I is equal to 9 to get these equations. For I is equal to 1, this is going to be the first equation, then 2, then 3, and 4. This is at I is equal to 2, 3, 4, and the last will be at I is equal to 9. If you observe, we can convert these equations into a tridiagonal system because of repeated values. So in the first case, this thing is extra. If we want to start over a column vector of unknowns from 1 to 9. So this is at 0, that's why we will move it on the right hand side. And same for the last equation, this is extra, and this is also known from boundary condition. So we will move it on the right hand side. And then we will form the system of going from u1 n plus 1 to un n plus 1, and this will be a tridiagonal system. And on the right hand side you can see that this came from the left hand side, and also this came from the left hand side, and all the other values are came from here. So if I write this system of linear equation in closed form, it will be like something A, because this is a coefficient matrix, all these values are known because D is known, and un plus 1 is the unknown vector, while the right hand side I will call it w to the power n, and this is also known for the first iteration because of initial condition, and then for the second iteration it is known from the results of the first iteration. And our goal is to solve this system of linear equations. And let's start formulating the code of Crank Nicolson method. Okay, to formulate the code, I am copying the code of BTCS method because it was also implicit method and it will help us a lot and it will save our time. So I'm just copy pasting it and then closing it and saving it as, for example, crank. Okay, so in this case, if we are solving this example that we just solved, the length to pain is from 0 to 1 and the time is from 0 to 0.02. So length is 0 to 1, so 1 minus 0, and for time it's 0.02 minus 0. Alpha is 1 in this case, space step is 0.1 while the time step is 0.01, and this is important, the d value here is alpha delta t divided by 2 steric delta x square. Space nodes will be like this again and the time nodes will be like this. So we will have one extra node of course. And then I'm creating mesh of space and mesh of time, like how many nodes will be there in space and time. So x will be zeros of n comma 1 because L divided by dx will give us 10, 10, 10 plus 1 will 11. So there will be 11 space nodes in total, and of course 3 space nodes, sorry 3 time nodes in total, 0, 1 and 2. And it's just we are creating these space nodes here, space mesh here, and this is time mesh here. This will just define the values of x at the particular node. For example, at the first node the value of x is 0 and at the second node it is 0.1 and 0.2, like this, and same goes for time mesh. Yeah. And here we are formulating the dimension of our U matrix, which is of matrix of unknown. So it will be m cross n because in this case it was m like 2 cross 11, two time values and then 11 columns. The left boundary condition was 0 in this case and the right boundary condition was also 0. So the first column of u and the last column of u will be 0, and the initial condition was depending on sine pi x, and here we are not doing the complete first row because the left and the right values are coming from boundary values, but they are also overlapping with the initial condition. If you can see from here, the values are from the boundary condition are 0, but the value from the initial conditions are also 0. So this was just defining boundary conditions and initial condition. Now let's come towards this A matrix and the right hand side matrix. So if we go here and see, if I call it A matrix, the dimension of A matrix is 9 cross 9, while if we see that the capital N was 11 because we have 11 nodes, but the value of A matrix was 9 cross 9 because we are skipping the first two, 0 and equation for I is equal to 0 and I is equal to 10. So in general, the dimension of A will be n minus 2. And let's call the right hand side matrix in this case as W, and the dimension of W will be again 9 cross 1, if you can see from here. And since we are making this code general, that's why we are using the general notations here. Okay, now for the values of A, there is a pattern, and which is like we have the pattern from the second equation to the eighth equation, but for the first and the last equation it was something different because there were like two values for the first and the ninth. So if I come here, a11 value will be 1 plus 2d in this case, not okay. So 1 plus 2d, while first row second column value is minus d. And similarly for the last n minus 3 column, and sorry, n minus 2 row, which is the last row, but uh, one back column is minus d, and last row last column is 1 plus 2d, minus d and 1 plus 2d. And for the remaining values there is a pattern like from I is equal to n minus I minus 1 will be minus d, which will be 1 plus 2d, and this will be again minus d. And for the W matrix on the right hand side, that matrix will change in every iteration. So let's see how we will deal with it. Since W will change in every iteration, so we will consider this in the time loop. So this is going to be our main loop, which is time loop for n is equal to 1 to m minus 1. So because m are the total number of nodes, and on the left hand side we will be using m, and on the right hand side we will using m minus 1. So that's why the loop will go towards m minus 1. Let's delete everything here, and now the w first value will be different from the remaining values. If I show you the right hand side source vector, the first and the last value of w is different, but for the remaining values there is a pattern. So we will deal with the first and the last value a little bit differently, and this is how we will deal with it here. So w first value will be 1 minus 2 static t into un2. So the indices are different from it. Like here we have un1 because our space nodes were starting from 0, but in MATLAB we cannot have 0 as a location, so that's why we will be adding 1 to these values. So here we have n1, so there we will be using n2 plus d static un2 here, but 3 in the MATLAB. And for the last values, d is multiplying with un1 and plus un plus 1, 1. So un1, 0 will be 1, and un plus 1, 1. And for these values there will be a pattern, so we will be using a loop for it. The loop will start from, for example, let's the indices of loop is I 2 to n minus 3, and w ith value will come as like this, because this is the pattern here. And since I is starting from 2, so we are using n the same things as here, because we have n1 here for the first iteration, but we will have 2 here because I is starting from 2. So I ended this loop at n minus 3 because the last value of w is also different from this pattern, and let's define it like this. So wn minus 2 value will be like this. Compare from here. So wherever we will see, since this is the ninth equation, so where we have 9, we will use n minus 2 of course, and for 10 it will be n minus 2 plus 1, which will be n minus 1, and for 8 it will be n minus 3. Sorry, since capital N is 11, so basically wherever we will see 10 here, it means we have 11. So 10 means n, capital N, and 9 means n minus 1, and 8 means n minus 2, because 8 is basically 9 in MATLAB. So we defined the right hand source vector for every iteration, and it will change in every iteration, and it will have values in the first iteration from initial conditions. Now, if we are using MATLAB built-in solver, the next step is very simple. Let's say we call the unknown as z. So we will just do a backslash w. It will solve this system of linear equation. But the computational cost will be greater in this case, and we will deal with it later in this video. We will use two techniques to deal with tri-diagonal system on the left hand side. The first one will be LU decomposition for tri-diagonal matrices, and the other one will be Thomas algorithm. So let's say first we are doing using MATLAB built-in solver. So z is equal to a forward slash w, and now u n plus 1 comma second to n minus 1 column will be equal to z. Now the reason why I'm using second to n minus 1 column, because I have, for let's say for this particular example, I will be having 9 values in z because I'm solving 9 linear equations. Now since the first column and the last column of u is the boundary conditions, so that's why these z values are for the inner nodes only. If you remember from here, these are for the inner nodes, not for the boundary nodes. And I will store these values in each row of the U to get my final system, or let's say this mesh, uh, this mesh. So these values. Okay, let's solve this. Let's run this code, and I am just not plotting these results for a while, and I'm not using semicolon here also because I want to see the outputs. Okay, so let's run this code, and these are the results for the first iteration. If you remember, this first row is from initial conditions, and this is the row that came as a result in the second iteration, and you can see the first and last columns are 0 because these are just the boundary conditions. And if if we are performing the first iteration, this is basically what we are solving. On the right hand side, these values came as a result of initial conditions. This source vector, which we are solving with this vector. So a backslash w is giving us these results, which are these results. And if you want to match these results, you can compare them from here. Now these will be used in the second iterations to compute the w, and the w for the second iteration will be this, and then we will solve it to get these results, and this will be the final form of the mesh. So these results are from the initial condition, the first iteration, the second iteration. The initial condition, first iteration, and the second iteration values. Okay, let's say we want to save the computational time and we do not want to solve this system of linear equations using a backslash w command. Now this command might be performing more operations and consuming more time, so that's why we will be using LU decomposition or Thomas algorithm. Let's say we will start with LU decomposition first. So one thing is clear, in case of LU decomposition, we won't be needing this A matrix anymore because we are decomposing this A into two different matrices which are L and U. So there won't be any A. Okay. And for LU decomposition of tridiagonal matrices, I have this document which will help us a lot in uh, to code this algorithm using LU. So for LU decomposition, uh, if we have this tridiagonal system, it will decompose the L and U matrices into this system. Now observe carefully the values in this L and U matrices that we need that will be different from this given A matrices will be these L values, L2, L3 up to Ln, and this V values, because these C values are already present in the A matrix and these are just the ones. Okay. Now how we will determine these L and U matrices? So basically U first value or V1 will be just the B1. So these B's in our case in Crank Nicolson method, I think you know them, these are just 1 plus 2D. If I am opening the document here, hmm, okay, yeah. So these are or B's in this case, the diagonal. These are just C's and A's are different. Sorry, same for us. Like these are just minus D's. Okay. So U first value is B1. Let's determine the dimension of L and U first. If I want to compute these L and U values, these all L2, L3 up to Ln and V1, V2 up to Vn. Okay. The dimension of A matrix was n minus 2, n minus 2. Okay. Let's say the dimension of L matrix is n minus 2, comma 1, because we only need the values L1, L2 up to Ln, and that's why I'm using the column matrix, not a complete square matrix. And let's call the U matrix as a V because we are using already U for the matrix of unknowns. Now the dimension of L should be like n minus 3 because there is no L1 entry. If you observe from here, there is no L1 entry here. But to be consistent with these values, I am like introducing L as n minus 2 because the L is starting from 2 but ending at n, and also V is ending at n. Okay, so First we will compute v first value, which will be v first value will just be 1 plus 2 static t b1, which is 1 plus 2 static. And then L kth value will be like this, where k varies from 2 to n, and v kth value will be like this. So we will be using loop here for k varies from 2 to n minus 2, because there are total n minus 2 entries here. And L kth value will be, okay, let's say L kth value will be, if we observe from here, it will be a kth value divided by v k minus 1 value. Now a kth value, all values are minus t's. So minus t divided by v k minus 1, and v kth value will be, b kth values all are 1 plus 2d in our case, and negative c kth values, all values are minus d. This minus will come as here, so plus, and L kth value. Okay, okay. So now we have those L and V values, and now we will be solving uh, two system inside this loop to get our answers. Let's see how we will solve those two systems. So we are not solving getting Z as A for backslash W, which means we will be performing this algorithm. So first we will solve Ly is equal to F. So F in our case is basically W, the right hand side, because here the F is the right hand side. Y first value will be the right hand side first value, and the right hand side is W. So let's say Y first value. I'm not defining the dimensions of Y, because in MATLAB we can work uh, with, without defining dimension of a matrix as well inside a loop. Y first value is basically W first value. Let's say what we have here. Y kth value will be like this, where k varies from 2 to n, and again I will be using a loop for it. K varies from 2, the last value is n minus 2, and y kth value will come as like this. The right hand side kth value minus L kth value static y k minus 1 value. The right hand side kth value minus L kth value y k minus 1. And then we will be solving the other system to get our final U matrix of unknown. And for this, we will know the last value, which will be u nth value will be y nth divided by v nth value. So let's say we are storing again the answers in a z. So z will be like, sorry, z last value will be y last value divided by v last value. And for the other values, we will be using backward loop. So n minus 2 is known, so we will be using from n minus 2, we are taking a backward step minus 1, we are going till 1, we are ending this loop. And how we will be getting z kth value now? This is how we will be getting z kth value. Y kth value minus c, all c values are minus d, so minus minus plus d, and this uk plus 1 is basically z, u small u in our case is basically z, so zk plus 1 divided by vk. That's it. And then we are storing the z in again for each row. The 9 values will be stored here. Let's clear it. And now we are running this again Crank Nicolson method, and the values are again same if you observe from here. So we solved the system using LU decomposition. Now the last part of this video, we will be using Thomas algorithm to solve this system. Okay. So for Thomas algorithm, what is basically Thomas algorithm? Thomas algorithm is basically this. In the first step of Thomas algorithm, if we have a tri-diagonal system and the right hand side, we can try to convert this left hand side into a upper triangular system by using the row operations and making this diagonal entries as one. So at the end of this first step, this system, this complete system will be something like this. Of course, now the right hand sides are different because there will be some plus and minuses, and but this diagonal will be 1 at the end, and these c's will be converted in something called gamma, and they will also be different because of dividing or some operations. Now how we will convert it into this, there is just basic steps. For the row 1, so basically in Thomas algorithm, our basic entries are gammas and rows because we are converting the right hand sides into rows and the c's into gammas, and everything else will be like 1 or zeros, which are not of concern. So if this system, since it is going till 6, will be 6 gammas and 6 rows at the end. So our system is of dimension n minus 2, so there will be n minus 2 gammas and rows. So now we are not solving it using LU decomposition, so let's call it, uh, we have gamma which is of dimension, and we have row which is of dimension n minus 2. This is not required, and this loop is also not required because we will be finding these gammas and rows inside the time loop because we will be solving there. Let's come here again. So since it was 6 cross system, and at the end of this, okay, sorry, so we have 5 gammas and 6 rows, 5 gammas and 6 rows. So the dimension of gamma will be n minus 1, less than the total dimension. And what we will be doing here will be different again. If I go back to the document and you observe this carefully, the gamma first and the row first values are different from the pattern of all the other values. So for all other gammas and rows, there will be a pattern, but not for the first value. Let's say we will not use loop for these values. And if you observe for the, like, for gamma 2 this is this row, and for row 2 this is this, and this pattern will repeat for gamma 3 and row 3. Okay, let's just say we are computing gamma 1 and row 1 outside the loop, and this is how we will be doing it. So row first value will be right hand side first value divided by 1 plus 2d, row first value, right hand side first value divided by b1. B's are all b's in Crank Nicolson are 1 plus 2d. And for gammas, it will be C1, all C's are minus D, and all B's are 1 plus 2D in Crank Nicolson. So these are just row 1 and gamma first. But for the other values, we will be using a loop. Now, since the gamma is going till n minus 3, so I will be using loop I2 from the n minus 3 because I will be using the same loop to calculate all the other rows and gammas except the last row. So the pattern, let's consider gamma 4 and row 4 for it. If this is gamma 4, it will be C4, but all the C's are minus D, and all the B's are 1 plus 2D, all the A's are also minus D. But if this is 4 here, this is gamma 3 here. If this is I here, it will be I minus 1 here. So for gamma I, it will be something like this. And for row I, if this is row 4, it will be right hand side fourth value minus A's all are minus D. If this is 4 here, this will be 3, I minus 1 here. All B's are 1 plus 2D, all A's are minus D, all gamma. So if this is 4 here, this will be gamma 3. If this is I here, it will be I minus 1. This is how we will compute gamma, but we haven't computed the last row value. I think the pattern will be same, but we used the loop because we use the same loop for all gammas, and so for the last value we will be computing it like this, row n minus 2, and this is the pattern here. Because for row I it was wi, so here for last row it will be n minus 2, and for if this is any I minus 1, that will be replaced with the second last, which is n minus 3. We computed the gammas and row. The next step in Thomas algorithm is solving this system now. To solve this system, if you see here, the last value of the unknown is basically the last value of the row. So our unknown matrix in this case is Z. So Z last value is basically the row last value which we computed just above it. But for all the other values, there will be again like back substitution, and there will be a pattern here, and this is the pattern for if this is the x fifth value, row fifth minus gamma fifth x6. This is x4, row 4, gamma 4 x5, x3, row 3 minus gamma 3 x4. So how we will write this? Of course, we will be using loop for it, and it will be something like this. For k varies from n minus 3 to with a backward step till 1, and z kth will be row kth minus gamma kth static zk plus 1, and we will be again storing this z into that row of the u. Okay, let's clear the screen again and now run this code, and again the results are same. Now this was the one example that we solved here. Let's solve something from a reference or a book. So I have a computational fluid dynamic book here with me, and in this book uh, there is this one example that he solved, and he asked to solve this example with these just values using Crank Nicolson method with two different step sizes, and he basically gave the result using this step size. Let's formulate this example first in our code. So in this example we have initial condition and boundary conditions like this. So for initial conditions, for boundary condition at at y is equal to 0. Okay, let's first define all these things step by. Length in this case is 40 millimeter, which in standard units will be 0.04. So length in this case will be 0.04, and time that he want us to obtain at 1.08 second. So the last time will be 1.08 seconds. He also gave us the diffusivity, the kinematic viscosity, which is basically this V, which is alpha in our case, which is 0.000217. 0.000217. Space steps, he asked to solve for space step 0.001, and the time step here is, yes, the time step will be defined here. So we will be using this case 0.01. Okay, and everything else our code will calculate it. The other thing that we need to change here are the boundary condition. The left boundary condition is 40 because he mentioned that u naught is 40, and here he mentioned what will be the boundary condition. At y is equal to 0, it is u naught, and y is equal to h, or y is equal to 0.04, where it is 0. And the initial condition, because this condition will overlap with the boundary condition, and we already take care of this thing, like we are like applying the initial condition on the inner nodes, like not the boundary nodes. And that's it, and then we will run this code. So let's clear screen. Okay, it take a lot of time because we are seeing all the u's here, and let me, because we cannot observe this u here carefully uh, or clearly, so I'm opening the u here. Okay, so this is basically the u values at the last time step. The last row is the values at the last time step, right? So let's say what Hoffman says. So he actually gave us the results using this, and the results are presented in this table. You can observe Crank Nicolson using these initials, and he just gave the values at some time steps, where the last column are the values at the last time step, which in our case will be the last row. Let's match some values here. 40, 38.523, 40, 38.523, and then last values will be 0, 0.5369, 0.53. So he gave the result up to 3 decimal places, but we have the results up to 4 decimal places. Now let's just say we want to compute the computational time of all three methods that we used. The first one is MATLAB built-in command, then LU decomposition, then Thomas algorithm. I saved this code independently for the example that we solved in HOFFMANN book, and let's run this code. So for to compute the computational time, we use CPU time command, which is basically not an accurate command. Usually MATLAB suggests to use time it command, but we can use the time it command only on function files, which we do not made in this case. It is not function file. We can convert this code into function file, for which you can watch my video in which um I explained how to create a function file in MATLAB. So let's run the first one, which is basically MATLAB built-in command, and the time end in this case is 0.0625. For the other case, I also use the clear R and CLC commands on every on the top of every code. This is LU decomposition code crank 2. It's 0.03, and for the crank 3 code, which is Thomas algorithm, it's 0.04. So CPU time command usually do not give accurate answer, so you can also try this time it command. And at the end, if you want to see the plots, you can also see them. Figure 1 and figure 2. The first plot is x uh, at last time step. So x versus u plot at last time step. The second will be at the all the times at the center of x, like at x is equal to 0.02. If in this case we have 0.04. So if you want to see these plots, you can run this again. Of course, in this case, the CPU time will be more because it's computing the plot. These are the two plots in this case. The method is unconditionally stable, so you can use any value of time step and space step. That's it. That's all about Crank Nicolson method. See you in lecture 7. Bye bye.